Now, the first two examples that I did were directly out of the book. This one is it's fairly close to what's in the book, but I'm trying to illustrate a few different things here. Again, we're trying to look at ways to make this fit into forms that we already recognize. And we see right away, we don't really like the fact we've got a 2x in here. We're going to make a substitution and say u at some point. We can see that. But also the fact that we really have, that's an issue here, is the fact that this is something over a split fraction with two pieces. Okay, we don't really like that. This is not unlike when we have, if you work with imaginary numbers before, you're not allowed to have imaginary numbers in the bottom of a fraction, those kinds of things. We need a way to make this so that this doesn't look like this. We want to be able to combine this so that it's a single term, if possible. Now, how can we go about that, to do that? Well, what we do is we multiply by the conjugate. Now, just like other types of algebra, when we are saying, okay, well, we need to, multiply top and bottom of this side of the equation by 6 or whatever else. Here, we multiply top and bottom. We can multiply by whatever we want. As long as it's the same on top and bottom, that fraction is just multiplying by 1. When I do that, of course, it's had no impact whatsoever on the limits. Doesn't have any impact on dx other than to say now I have 1 plus cosine 2x in the top, dx. And what do I have in the bottom? Well, this is a FOIL method, right? First times first is 1. Inner is 1 times minus cosine 2x. Outer is cosine 2x times 1. Those cancel each other out. Plus cosine 2x minus cosine 2x, nothing there. And then minus cosine squared of 2x. Now, why is that better? Well, again, thinking of this sine squared x plus cosine squared x equals 1 identity, that, if I rearrange this, subtract cosine squared x from each side, that's what I have. It's sine squared. Now, in this case, I said x over here. It's 2x. It's whatever the argument is here. So the denominator becomes first. And then the denominator just becomes sine squared of 2x. Now, is that good, bad, or indifferent? Well, I don't know yet. I have to do some more work in order to see where I get to. But it certainly makes it so that my denominator is a single term as opposed to a split denominator. And what that allows us is that we can now rewrite this as two separate fractions. 1 over sine squared 2x plus cosine 2x over sine squared 2x. So I'll do that here. So it becomes two separate integrals. Now again, I have to start thinking in terms of, okay, now I want to try to get these, even though these look like they're trig integrals, it's not a trig integral just like sine x or something like that. It's more complicated than that. But I want to get this into a form that fits into those 22 or so integrals that we've already established ways to handle. And so I look at this and I say, well, what needs to be done? Well, what is 1 over sine squared? Well, 1 over sine squared, that's cosecant squared. So I can simply rewrite this one as cosecant squared 2x dx, cosecant. Now, cosecant squared, in the same way as secant squared comes from tangent, cosecant squared, well, you'd actually get negative cosecant squared if you took the derivative of cotangent. So this is going to go to being a cotangent. We're going to have to do some substitution there, etc., but to get rid of the 2x, but we'll deal with that in a minute. But that's getting in a form that we know how to deal with it. Now, what about this one? I've got both sine and cosine. That seems messy, okay? I could rewrite this as cotangent over sine, because I could use one of the signs and say, well, cosine over sine is cotangent. Cotangent over sine, that doesn't help me at all. I could write this as cotangent, since it's 1 over sine, I could write it as cotangent times cosecant. Now that has a little bit more promise. So, well, if I rewrite this as cotangent times cosecant, all right, because what do I have? I've got cosine of 2x over sine 2x times sine 2x. That's what sine squared 2x means. And so if I look only at this piece, that's cotangent x, cotangent 2x in our case. And if I look only at this piece, that is cosecant 2x. So that's what I'm going to do, is I'm going to rewrite it that way. And say that's cotangent 2x, cosecant 2x, dx. Now I apologize for the lack of space. I'm going to sneak up here and finish this one up rather than going down deeper onto the board. I'm going to say, okay, what do I need to do? Well, I don't want this whole 2x thing. I want that to be u. And so I'm going to make a substitution. I'm going to say, well, I'm going to let u be 2x in each of these cases. So if u is 2x, du dx is 2, which means that dx is du over 2. That's one part of the substitution. But what else? Also, I have, this is in the x world, I'm going from pi over 6 to pi over 4. What is u of pi over 6? Well, u of pi over 6, if I put in pi over 6 for x, I get 2 pi over 6, which would be pi over 3. My limit's going to change to that. And what is u of pi over 4? Again, if I put in u of pi over 4, I put pi over 4 in there, I get pi over 2. Oh, I'll get myself in trouble. I just made up those limits. I might. So pi over 2, pi over 3, those become my new limits. And now I rewrite. I'm going to look at the first one. I have the integral from pi over 3 to pi over 2 of cosecant squared u du. And cotangent, the derivative of that gives you negative cosecant squared, so this integrates to negative cotangent. That part, negative cotangent u, where I'm going to evaluate at pi over 2 and pi over 3. And cotangent, sign's okay there, all right. So that's just the first part there would become negative. Well, what is cotangent? Cotangent's cosine over sine. So this is cosine of pi over 2 over sine pi over 2 minus cosine pi over 3 over sine pi over 3. Cosine pi over 2, that's straight up on the unit circle. Therefore, that is 0. That term just goes to 0. And this other term, what do I get? Well, I get negative, a minus and a minus becomes a plus. Cosine of pi over 3. Pi over 3 is where x is 1/2, cosine is 1/2, and sine of pi over 3 is where sine is radical 3 over 2. So I end up with 1/2's cancel, and that gives you 1 over radical 3, which is radical 3 over 3. So that's what this piece becomes, radical 3 over 3. Now again, I'm going to make the same substitution. So, whoops, and I left out a 1/2. There should be a 1/2 everywhere here, because that was du over 2 here, and therefore there's a over 2 all along here. And so end up with 1 over radical 3 over 6 for that piece. Okay, same thing with the other one. Same substitution, because I still have this 2x, which is irritating me. And I say, well, I have the integral of, and all of this, same change here, so I have from pi over 3 to pi over 2. And that is cotangent 2x, or I'm sorry, cotangent u, cosecant u, du over 2. Pull the 1/2 outside here and say cotangent u, cosecant u is, you get negative cotangent cosecant u when you take the derivative of cosecant. And so I'm going to say this 1/2 and then the negative cosecant u, where u is going to be evaluated pi over 2 and pi over 3. Again, I'm going to pull the negative 1/2 outside. And I have cosecant of u. Well, cosecant is 1 over sine. So this is 1 over sine evaluated at pi over 2 minus 1 over sine evaluated at pi over 3. And sine of pi over 2, that's straight up on the unit circle. That's where sine is 1. So this is 1 over 1, it's just 1. And pi over 3, we just said in the previous one, we evaluate sine of pi over 3 is radical 3 over 2. So this is 1 over radical 3 over 2. And of course, we can clean this up and say we've got 1/2, 1 minus 2 over radical 3. That's 1/2 minus 1 over radical 3, which is 1/2. 2 is canceled there. Minus radical 3 over 3. And that's what this part over here becomes. Except I lost the minus sign. I should have been a minus there, and there, and there, which makes it like this. So that's a plus, and that's a minus. And we could clean that up and get common denominators, etc. if we wanted to, but that's basically where we get. The key takeaways here are when you see something like that, you are able to get it so that your denominator is simpler by using conjugate here. And then you go ahead and make these substitutions, just like we've talked about all along, and you can get where I did here.